Hello, everyone. We are Team C, and today we will be presenting our progress on our ultra-high bypass ratio turbofan engine design. Our team is comprised of 6 people. From the top left is Alec, then myself, Cole, Benjamin, Kevin, and Peter. To begin, we will first discuss engine requirements and the design targets for this project, starting with the problem statement. So, the problem statement is to design a turbofan engine for entry into service by 2025, and there are a couple key requirements that we need to hold to. The engine shall be designed for use on a twin-engine wide-body aircraft, shall incorporate a geared fan, and use a 3-spool core. Additionally, the use of a high bypass ratio is recommended. All of this is done to achieve overall reduction in fuel burn by achieving a higher propulsive efficiency at cruise conditions. But it is important that we design for off-cycle performance as well. Additionally, we are required to retain the core of the provided baseline engine, which is a generic 3-spool design from gas turbine. Kevin will discuss the rest of the design requirements, starting with the flight envelope.
Thank you. So the flight envelope for the aircraft is the following. At takeoff conditions, we're assumed to be at standard sea level with a required power of 200 kilowatts, which was increased from 50 kilowatts in the report. At cruise conditions, we'll be at over 12,000 meters and Mach 0.85, which is a standard value for passenger aircraft. Our total range will be a required 17,600 kilometers, and we can go ahead and go on to the next slide, which will be over the engine design information. So the requirements for the engine include a bypass ratio of 15:1, which was increased from 9.3:1 in the report. Another requirement is the use of a geared fan with the mass of the gearbox equivalent to 0.0036 kilograms per horsepower transmitted. The overall pressure ratio of the engine is 60:1, increased from 50:1, and the turbine inlet temperature is a little over 1900 Kelvin, which is increased from 1784 Kelvin. This will require some advanced materials or cooling techniques, which we'll discuss later in slides. And rounding off the engine requirements are the casing diameter and engine length at nearly 3 and 4 meters respectively. I'll now pass it off to Ben to talk about the engine matching in gas turbine.
So the first major milestone of this project was to analyze the baseline engine that was provided in the request for proposal. By replicating the results of this engine analysis, we can confirm that we have installed gas turbine correctly and is operating as intended. This exercise also demonstrates that the team has developed a working knowledge of gas turbine. This analysis was conducted by inputting the relevant engine parameters from the request for proposal into gas turbine's 3-spool turbofan model. Our results matched reasonably well with the results given in the request for proposal. All the output values match pretty well. Most notably, total thrust and thrust-specific fuel consumption have less than a 1% error in the calculated values. This slight discrepancy can be attributed to the newer version of gas turbine that we are using since the request for proposal was originally published. The engine architecture that was used in our gas turbine analysis matched the one given in the request for proposal. And gas turbine is also able to provide TS diagrams for different engine analysis to provide a further understanding of the cycles of the engine. With this first analysis complete, we can be more confident in our ability to analyze improvements to this engine in our future analyses.
All right, so before we go any further into understanding that design, we want to take a quick detour to look at our schedule, both how we got to this point and what we're looking to accomplish in the future. We organize ourselves using the Gantt chart that you can see. It's broken up into 3 major sections. First, understanding the initial design, the requirements, and the past designs that have been done in this area. Then we're preparing for our intermediate presentation through operating gas turbine and getting that functional on all of our computers, working with that program, and then assembling a full working engine based off the RFP. Following this, we have preparation for the final presentation, which involves modeling engine improvements, deciding which ones of those improvements are feasible, comparing those improvements against the base engine concept, and selecting which one of those are most optimal for improvements to the engine design. Additionally, There are some important dates we have outlined at the bottom that we just have to be aware of as we're going through our project to make sure that there aren't any conflicts with other elements of this class. As for what we have completed already, we have gone through the initial design process phase, making sure that we have all the requirements needed for this engine proposal, and getting a good sense of what options exist from past designs that we can incorporate into this engine. We've also worked with gas turbine on our computers, as you've seen before, and gotten it to match with the given 3-spool design. And then we've started to think about what improvements we can make to that cycle, which we will go into in a little bit. That is going to be mostly focused on what we're going to be doing in the future, however, as our plans following this presentation mostly involve determining our engine improvements, which ones we want to model, running them through gas turb, and evaluating them against each other to see which one of those improvements would be the best one to select to improve our engine design. And then we just have a few things on the bottom there we just have to keep track of in order to keep on top of all of our requirements for this course.
I will take it from here and talk about the preliminary design concepts that we have. So overall, we have got 4 preliminary design concepts that we will evaluate to see how they improve engine performance. The first of those is interstage cooling on the compressor. We're also going to evaluate liquid-cooled turbine blades, a recuperator, and ceramics matrix composites. The plan is to perform sensitivity analysis on all 4 of these concepts to select which one or combination of concepts will give us the best engine performance. So we'll go through one by one and perform trade studies on each one, implement them into the engine model, and then also implement combinations of the concepts to get the overall best engine performance we can. So the first concept of interstage cooling, the idea is to take air from between the IP and HP compressors and cool it down so that you can boost the efficiency of the HP compressor. A couple of heat sink concepts that we have are using the bypass air, which, because we're going to a higher overall bypass ratio, is a very attractive option. The other concept we have is to dump that heat into the fuel. It's worth noting that intercooling, while it's used in some industrial gas turbines, as far as we know, it is not utilized in an actual engine flying around. So while it is an existing technology, it's been used on some demonstrators, but not on any known engines flying around out there. So the trade studies we're going to use to evaluate this concept, the benefit it can provide for the cycle is increased performance, but the challenges are increased engine weight because we'll be adding a heat exchanger to the engine, and then also any potential impacts on pressure loss in the bypass stream or the fuel system. So we'll weigh those things together when we evaluate the interstage cooling.
The next approach that we will discuss is the use of liquid-cooled turbines, specifically using fuel as the active working fluid. Active cooling has been used since the 1940s to increase the turbine inlet temperature in engines, thus overall improving the thermodynamic efficiency of the engine cycle. Such cooling is almost exclusively performed using air as the working fluid, specifically in a film cooling configuration, where air is routed as an insulative blanket around the turbine blade, protecting it from the hot gas flow. However, we propose the utilization of fuel regenerative and film cooling as a possible performance improvement, and we do so for a couple reasons. Firstly, whether fuel cooling is used in conjunction with air cooling or instead of air cooling, the superior heat capacity of fuel relative to air allows for the overall reduction in coolant consumption in the engine cycle. This cooling performance can further be improved by utilizing the high latent heat of vaporization that is intrinsic to liquids. Furthermore, by reintroducing the coolant fuel into the flow, one recuperates the energy lost in the cooling process, thus allowing for an increase in thermodynamic efficiency. But furthermore, the reintroduction of fuel into the core flow allows for the continued propagation of the combustion process through the turbine stages. This, in turn, allows for the possibility of a constant temperature expansion process similar to that seen in Ericsson's cycle, which in turn allows for an overall increase in thermodynamic efficiency. It is, however, worth noting that while liquid cooling in various different forms has been an object of study since the 1940s by NASA, industry, the DoD, etc., It is important to note that liquid cooling is not used in engines in active service. Again, air cooling is more or less ubiquitous in this regard. But due to the increased demand for engine thermodynamic efficiency and environmental friendliness, the advantageous qualities of liquid cooling make it an attractive approach to consider.
The next concept that we're taking a look at here is a recuperator. And the concept here is to take some of the hot exhaust gases and run them through a heat exchanger to recover some of that unused thermal energy in the flow. The other side of that heat exchanger is used to transfer heat to the air between the compressor and the combustor. By doing so, we're able to replace some of the fuel burn with that exchanged heat to improve our overall efficiency. This is most commonly used in mid-size electrical power generation gas turbines and is not on any flight systems that we know of. To evaluate this concept, we have a couple of ideas on how to model this during our selection process. The first is through the reuse of regenerative cooling analysis codes for rocket engines. And the second idea is to perform CFD with ADS CFD by modeling the coolant tubes as simple ducts with a known wall temperature profile. To choose between these models, we need to select a specific heat exchanger design, which is currently in process. The primary challenges with this design are weighing the benefits of the increased efficiency against increased weight from this system and possible impacts on the amount of thrust generated by modifying the exhaust flow. I'll hand things back off to Kevin to finish up the presentation.
Alrighty, so in order to increase the turbine inlet temperature for this engine, we can utilize ceramic matrix composites. So ceramic matrix composites are utilized to increase the maximum temperature at the outlet of the combustor without passing the metallurgical limits of the turbine downstream. CMCs are made of silicon carbide fibers woven into a silicon carbide matrix. This makes them incredibly strong with high heat resistance and mechanical strength. These are currently used in the LEAP engine's high-pressure turbine shrouds and have over 4 million hours of proven flight time. There are plans to replace more components in future engines with these CMCs, and they've been used previously in the nozzle section of military jets in the past, but manufacturing issues have prevented them from being fully utilized in the civilian sector. So luckily, large investments in this technology by GE Aviation have ramped up production and manufacturing over the past years. So we can actually use some of this technology in our engine. Some big advantages associated with CMCs is a 2% reduction in fuel burn, weight reductions up to 50% in the turbine compared to traditional nickel alloys. And this is just because the material of CMCs is much lighter than the nickel alloys that are used. And then also a reduction in needed turbine cooling flow and 20% higher maximum operating temperature. That's the end of Team C's presentation. Thank you for your time and attention. And if there are any questions, you can either email us through Outlook or message us on Teams. So thank you.